Hello and welcome. This presentation is focused on the simulation and visualization of deep water asteroid impacts. Asteroid impacts are rare but potentially catastrophic events with significant implications for the environment and human safety. In this project, I utilized a dataset from the Los Alamos National Laboratory to simulate and visualize the effects of an asteroid striking deep ocean waters. The goal was to analyze and effectively communicate the environmental consequences of such an event. Through visualization techniques, we can better understand how these impacts unfold and their potential risks. Upon navigation to the Los Alamos dataset website, you will see that there are no download links for the .vti files that we want to use for our visualizations. However, have no fear, we can download these files using a simple Python script. Upon examining closer, the dataset used in this project simulates a high-velocity asteroid impact in a deep water environment, capturing three primary phenomena. Number 1. Crater formation. The impact creates a significant cavity in the ocean floor, resulting in complex crater structures. Number 2. Water displacement. The force of the impact dissipates large volumes of water, generating waves that could potentially evolve into tsunamis. Number 3. Shockwave propagation. The energy from the impact generates shockwaves that travel through the water, influencing marine ecosystems and potentially impacting coastal areas. These phenomena form the basis of the visualizations created in this project. To effectively visualize the phenomena, several techniques were employed. Isosurfaces. These represent surfaces of constant pressure within the water, making it possible to identify pressure distribution caused by the impact. Volume rendering. This technique visualizes the changes in water density, helping to illustrate the formation of the crater and its surrounding effects. Streamlines. These depict the flow of displaced water, showing patterns and velocities of movement caused by the impact. Ray tracing/path tracing. Advanced rendering techniques were used to produce realistic lighting, reflections, and refractions within the visualizations, enhancing the perception of depth and material properties. The visualizations were animated over time, enabling a clear depiction of the sequence of events from the moment of impact to the eventual dissipation of energy. These techniques work together to provide a comprehensive view of the dataset. This project utilized several key features in ParaView to achieve the final results. Number 1. Time-varying animation. Animating the progression of the impact allowed for a detailed observation of how the crater formed, water was displaced, and shockwaves propagated over time. Path tracing was used to enhance the realism of the underwater environment by simulating light interactions with the simulated medium. Number 3. Particle tracer filter. This filter, not covered in class, was utilized to depict the motion of several individual particles displaced by the impact, offering additional insights into the material dispersion. Both volume rendering and isosurfaces were used to visualize shockwave propagation, with each technique highlighting different aspects of the data. Volume rendering excels at showing the gradual variations in water density and pressure throughout the region, offering a continuous and detailed view of the shockwave's intensity and its dissipation over time. Isosurfaces, on the other hand, highlight specific thresholds of pressure or density by visualizing them as distinct surfaces. This allows us to pinpoint and track the boundaries of key phenomena such as the peak pressure regions or progression of crater formation. This project builds on prior research in the field. The study numerical simulations of impact cratering and water explored the physics of crater formation during high-velocity impacts, providing a foundational understanding of the forces at play during the initial stages of impact. Similarly, modeling deep water impact events and tsunami generation focused on the potential for wave formation and tsunami generation resulting from underwater impacts. This research emphasized the importance of visualizing water displacement and shockwave propagation for risk assessment. These studies informed the choice of visualization techniques and provided valuable context for interpreting the results of the project. Here's a montage of the visualizations that were created for this project. This concludes my presentation. Thank you.